I will talk a little bit about not a little bit, quite much in fact, about the core technology of Hegel. We have a patented technology that we call the Sound Engine technology. It is an adaptive feed-forward technology, and it's used to make a bigger dynamic range to remove distortion in a music signal. I will explain in a simplified way how we do this. Normally, the last years it's been a lot of talking about hi-res, playing hi-res in music systems. 24-bit, 192 kilohertz. But what's the point in playing hi-res 24-bit? It's a lot of dBs in dynamic range. 24-bit is typical, maybe 140 dB. But normal amplifier technology doesn't have dynamic range for bigger than 16-bit. So really, to get the best out of hi-res audio, you need better amplifiers to really be able to preserve as many bits as possible. So the amplifiers will limit the hi-res files normally. The Hegel technology will, of course, be quite much better than normal amplifier technology when playing hi-res files. I will tell a little bit more about this. We can have a look at how a normal amplifier has been built for many years, like I think about 1970. Most analog amplifiers has been more or less the same. An amplifier is normally divided in some different stages. To simplify, we'll just put on, okay, here's the speaker. Okay. So here's the output. And here is the input. And these are some internal amplifying stages inside the amplifiers. Normally, you're using transistors in these different stages to amplify the signal. You could use tubes, of course, some like tubes. For something, it's for guitar amplifiers, tubes are wonderful. But for high-end clean sound, tube amplifiers are not really the best way to have big dynamic range and really low distortion. Okay, so inside of these blocks, this is the input stage. This is what we call the VA, the voltage amplifier stage. And this is the power stage. That will drive the CAF. So, let's say the input stage has some gain. This is a little bit also a simplified mathematics rehearsal. So, the input stage has a voltage gain, or let's say, we make it simple. So we say 10 times. the input stage will amplify the input signal by 10 times. Okay? So we need a letter for the input voltage. Any good choices? A? Why not? Why not? So the input is an A. Then this amplifier stage will add some distortion. So we call this distortion from the first stage, we call D1, distortion 1. Okay, the voltage amp will obviously gain the signal by more than the input stage, let's say 100 times. Of course, the voltage amp will also have some distortion. It's the stage number 2, so we'll call it distortion D2. Why not? Okay, and then we have the power amp. The power amp actually normally has unity gain, that is 1 time of gain. Because it has the hard task to drive the high current, and then you normally use the transistors for current amplification and not for voltage amplification. So the last part has 1 times amplification, but still there is some distortion. D3. Okay. So let's see at this point after the first stage. What is the signal? You have the input is A. You amplify it by 10 times. Okay, so here we have 10A plus distortion from this part. Okay. So this signal is then the input signal for the next stage, right? We feed this signal in here, and then we will see what happens. Okay, so this is the input signal. We amplify it by 100. So here we have 1000 A, right? Plus 100 D1 plus D2. Okay, so then this is the input to the next stage. What we see is for every stage inside the amplifier, the problems from the previous parts will be amplified. So it will add up for a lot of different distortions, and the distortions will be amplified by the different stages. So in the end, you have a lot of strange distortions that really is not related to the original music signal. So this is the basic problem of amplifying a music signal. And these distortions, they are not static, they are dynamic compared to the frequency and the tone. So some instruments will have some kind of distortions, and other instruments other kind of distortions. So this will be a dynamic distortion based on both level of the signal and the frequency of the signal. So this is a complex distortion, many kinds of distortions. Harmonic distortion, intermodulation distortion, kickback distortion from the speaker when kicking back to the input, a lot of different distortions. Yeah. Normally, distortion is reduced by feeding some part of the output signal to the input. So this is a feedback loop. Okay, you take part of the output, you use some resistor to control the gain. Yeah, sorry. Here, So you take a part of the output and feed it into the input to try to reduce the distortion. And this is a good way, in theory. Problem: when the signal goes through an amplifier stage, there is some time delay through one stage. Yeah. So the input stage has a T1, the voltage gain stage has a T2, and the power amp has a T3. So here we have a delay that is the delay at the output is T1 plus T2 plus T3, of course. So the signal here is delayed compared to the input signal. So what you try to do is to reduce the distortion with a delayed signal. That means you really cannot fix the problem after the problem has been there. You can fix part of it, but you couldn't fix all. It's just like if you crash your car, you will have a dent in the car, you know. You could hammer it out with a hammer, it will be better, but it will not be straight and perfect.
Can't you build in some buffer so you can align the timing problem?
Yeah, sure. You could put. Well, actually, you could. But then you need some negative delay. And it's difficult. It's really hard. Because how to make a delay that is negative, I don't know how. Probably you'll get a Nobel Prize if you could find it.
Time travel. I'm not going to take a chance.
No. But it's a good idea. Yeah, it is. Really. But I'll show you later on how we do to get out of this this problem. Yeah. So main problem is if you try to fix the problem after a problem has appeared, it's difficult to get rid of it. It is. It's just like a factory. It's much better to make a clean factory than a polluting factory and try to reduce the pollution afterwards. It's the same way.
Any questions about this?
Yeah, good. So then we will have a look at what we do with the sound engine technology. We just look into one of the gain stages to make the explanation more easy. So here we have one gain stage. We have one transistor inside here. Also, to make the mathematics more easy, the gain of this stage is 1 times. Then the calculations will be more easy to understand. It can be any gain, but then it will be more complicated to show how. Okay, so the input is still A or B?
Whatever.
Yeah?
B if you want.
B? Okay. Distortion is still
D1.
D1. And the delay is
T1.
T1. Okay. So first we have an analog computer that subtracts the input from the output. So what is the output? It's B times 1 plus D1. So here we have B
D1.
plus D1. This is the output. Okay? So here we all have the same here. B plus D1. And then we subtract the B. So here we have only the D1. So now we know exactly what is the distortion from this stage. And this is quite good knowledge to have if you want to take away this distortion. We put this distortion signal into what we call a threshold. Detector. It will decide if the D1 is big compared to the signal level and the signal frequency. So it's really an analog computer that will decide if this distortion is so high in magnitude that we need to correct or eliminate this distortion. If the distortion is very, very small, then it's not possible for the ear to hear it. So this will only work when we need to do the feed-forward system.
It's really a dynamic system.
It's a really dynamic system all the way, and it doesn't really know what kind of distortion. It doesn't care about the kind of distortion. It will eventually eliminate all kinds of distortion, like its crossover distortion, harmonic, intermodulation, any kind of distortion. This system will handle. Okay, so what do we do? We put, if the threshold detector finds, okay, this distortion is possible to hear, we have to fix it. We put out the distortion signal here, and we multiply. In this stage, we multiply with -1. So here we have the minus D1. And here we have a summing stage that will add these two signals, plus and plus. So we have the B plus D1, and we add the minus D1. So we have cleaned perfectly.
Can you compare it to a balanced system in some way?
No.
It's really different.
No, a balance system is mainly mainly made so that external influences will couple same size of problem into both phases. Then you can reduce it. Yeah. What is important here, you know, for the amplifier block, we have the T1, and as you asked about previously about the delay, we match the delay of this part and this part, so this part also have exactly the same delay. So the signal and the minus distortion signal is perfectly aligned in time, so it will cancel all distortion up to about 300 kilohertz. Yeah. It's a fast system. And this is also the main difference between what we now call the new generation of sound engine. We use it in the H360, and we use it in the Rust, the new integrated. And the new generation of sound engine has a faster system for correcting this kind of error. So it will limit or reduce distortion at higher frequencies much more than the older Hegel systems. What this system really does is it will preserve the timing and the distortion of the signal. Especially with the CAF speakers, you know, they are the single point source where the timing information is really important. And the Hegel amplifiers, because of this system, will preserve the timing of the signal. It will not smear the signal in time dynamically. That's, I think, one of the main reasons why CAF and Hegel work so well together. Is because of this, and also because of the damping factor on the output of the Hegel amplifiers, also because of this feed-forward system. So good control on the bass and really good time precision and low distortion. Main points.
This is the first stage. So you now the signal is going into the second stage.
Yeah, this is just the principle of how the sound engine works. So we could use it in different stages and different configurations. So this is just only to show how is the principle working.
Correct. The Hegel amp after the first stage, after the second stage.
It's a little bit different from the different products. So, but we used a system where we need this kind of elimination of the distortion.
And that's all in that small chip.
Yes.
Wow.
Which you invented.
Ja.
En voor de eerste keer, het is dus in Duits, toen voor de eerste keer dit verhaal dus vertelde, toen heb ik IJ van Audiosurf meegenomen. Die heeft ook wel redelijk verstand van dat spul. En die komt dus hier en die krijgt de hele uitleg. En die wil dat apparaat dus weer verstand te bekijken. Maar dat gaat dus niet, want die soundmodulen, die zit ingekapseld in hars. Dus je weet niet wat erin zit. En ook in het schema zit een keurig blank spot in. Maar het schema is helaas, dat is het patent van Hegel.
Actually, the performance of this system is so good that each and every channel of every Hegel amplifier is adjusted manually by using the audio precision test system. So every system is calibrated. Both channels of any Hegel amplifier is calibrated to have the best possible, lowest possible distortion. Yeah. So firstly, the sound engine module I showed you, the small blue component, is trimmed by laser in production. And then, because there are some small variation in the power transistors, there is also a manual adjustments for every product manufactured. So they are really precision instruments. That's also, I will also explain a little bit about the crossover distortion. Because dynamic crossover distortion is probably one of the worst kinds of distortion that is difficult to get rid of. You could reduce harmonic distortion, you could reduce intermodulation distortion, but dynamic crossover distortion is very, very difficult to get rid of. Do you know about crossover distortion? Yeah?
One transistor, the other one.
Yeah, I can explain.
Very good.
I'll explain for you. In a normal push-pull output stage, for all big amplifiers, you need a push-pull output stage. So the output will be controlled by two transistors. So here's the speaker. So when the signal is positive, you have if you just explain it by sending in a sine wave, the sine wave will have a zero line. When the signal is above zero, this transistor will put the current into the speaker and to ground or zero. So it will take the power from the power supply, the plus 50 volts, and it will source the current down here. That's in this area. Maybe I could use another color, but oh. Normally the blue one is the other side, but yeah, not today. Okay, so here Okay, we'll try. When the signal is below 0, negative signal, the current will go from the minus 50 here through the speaker and to 0. So this will pull the current up, this will pull down. Then there is a problem exactly here, because these two transistors will have to, in a way, negotiate between them. When should I let the signal go, and when should the other take over the signal? So this transistor must shut down, and this must start up while transferring the signal from positive to negative. And this is quite difficult to do this, actually. If we look at the example, if the top transistor shuts up too early, and then the bottom transistor starts too late, then you have a signal that looks like this. So you have the signal here, and for some time there is no signal, and then it goes down. That's what you say, you have too little bias in the output stage. So the complete amplifier is shut down during this phase. There is no output signal. The other way around, if this transistor still source current while this transistor starts, then you will have too much current. So you will have also a transition, but in this direction instead of this direction. So here you have a period where you flow a lot of current, but neither of these are correct. Problem with both these is they will generate a lot of high order odd harmonic. This is a harmonic distortion that is very dissonant for the ear. It sounds like non-harmonically related frequencies. Like the second harmonic is 1 octave up. The fourth harmonic is 2 octaves up. So they are musical. But crossover distortion is typically 7, 9, 11, 13, high order, and it's really ugly. And it's the main reason of the harsh sound of transistor amplifiers, because this is really difficult to get rid of. It is. Normally, what the manufacturers do is to set up some idle current or bias in the output that will make this, so you can adjust here, you can adjust the voltage between the bases of the transistors, and you could adjust until it will match perfectly. It's possible to do. So you have a bias adjustment. So how to adjust the bias? The problem is the current in the transistor is dependent on the temperature of the transistor. So if the temperature goes up, the current will also go up in the transistor. And the main problem when you play musical signals is that the power in the upper and lower transistor is not, they don't have the same temperature because they have a signal that is not symmetrical. If you look at the sine wave, it's perfectly symmetrical. It has the same area above and below 0. So the power here is identical, but a typical music signal could be like this. So it has a lot of power on the positive side. So this transistor gets hotter, and this transistor gets colder because it has less power.
It's going to shift.
Yeah, and this is going to shift as a function of the music content. Yeah, music signal. Yeah. So like this is a typical maybe a kick drum or a snare drum. It will go like this. So dynamic music will always make different temperature for the transistors. This is the headache of the dynamic crossover distortion. Normally, the best you can do when you make a normal amplifier is to say that, okay, in the factory we will adjust this bias using some sine wave. Let's say we'll put out 10 volts, use a sine wave for 1 kilohertz, and we use a 4 ohm load. 10 volts, 4 ohm load, 1 kilohertz. And then we adjust the bias. And then for this signal, it's perfect. It's really, really perfect. It's very, very good when you play 1 kilohertz sine wave. It's perfect. You don't need anything else. It's absolutely perfect.
Accept that.
Yeah. But problem is the distortion will go like this. So when we adjust with the 1 kilohertz signal, we adjust so the distortion we have the best point, the lowest distortion for the 1 kilohertz. But when we start to play the dynamic music signal, the temperature of the transistors will change, and the bias will go up and down, and you will have dynamic crossover distortion like this. And also there will be some memory effect because of the heat sink will store some energy from the transistors, and the inside of the transistor will have a different temperature than the heat sink. So it's a quite complex system, really.
I once saw a manufacturer that matched its transistors for temperature, but that doesn't solve the problem of asymmetric waveforms.
No, it
course.
doesn't. It doesn't.
No.
So it's really difficult to do this. And I think this is the main problem of amplifiers. It's the dynamic crossover distortion, because there is no standardized way of measuring this. You don't see this in a stereophile lab report. You don't. So
Just move to class D then.
no, but the beauty, if we go back to here, if we go back to the sound engine, we know that the crossover distortion is one kind of distortion, and the sound engine system, it doesn't care. How does the distortion look? It doesn't care. It will fix this kind of distortions. So it will fix the harmonic distortions, the intermodulation distortions, and also the crossover distortions, especially the dynamic crossover distortions.
Did you know that the sound engine could fix that?
Yeah, it can.
Wow.
Yeah, it can.
This is a headache for a lot of
It is. It is. Yeah.
designers.
Yeah, it is. It's a real headache. But I think this is part of amplifier testing that has been very little, most testing is done with static symmetrical test signals everywhere, and it doesn't really show the performance when using asymmetrical signals. It doesn't. So this is quite cool.
It is.
Ja. Of course, I also said earlier that this system will also fix the damping factor. The damping factor of an amplifier is really how well the amplifier normally you have some feedback, maybe. The speaker is inductive. It's a big coil. So when you push a very high current into the speaker will kick back. Try to kick back because a big inductor will always try to keep the current constant. That's the task of the inductor, really. So the speaker will kick back to the amplifiers. And what happened with the kickback? It goes partly into the output stage, and it goes partly into the feedback stage and into the input. So the kickback from the speaker will damage the sound of the amplifier. So you want to make the output of the amplifier as low impedant as possible, so you will kill the kickback. And the Hegel amplifiers use also the sound engine to have a very high damping factor that will control the woofers in a very good way. So this is part of the sound engine.
How high is the damping factor?
Normally on the older Hegel amplifiers, they are around above 1000. On the newer, like the H360 has about 4000, and the Rust have 2000. Yeah. So the damping factor is so high that this is not a problem anymore, really. So the output impedance is really low.
And it's across the whole range, because a lot of the specifications say 1000 at so many kilohertz.
Yeah. Well, really, the damping factor will go down at the very high frequencies, but there you don't need it because the kickback is in the low frequency, really. Yeah. So, but yes, the damping factor will go a little bit down because of the inductance of the wiring inside. Yeah, the amplifiers from the power stage and to the speaker connectors. There is some small wires. And this will limit the damping factor at very high frequency. Yeah, they will. But it really doesn't matter because you don't need the damping factor just there. Yeah, that's basically in an easy way explanation of the sound engine system. Well, Class D. Class D has been used for many years now. I think the first Class D amplifier I saw was for professional use, probably around the middle of the 80s.
Oh, wow.
Yeah, 84. They worked occasionally. They had serious reliability problems at that time. And the main point of a Class D amplifier is that it's a switching amplifier. Okay, so an analog amplifier will have modulate the output, so you really have a copy of the output here. But a digital amplifier is a switching amplifier, so the output will be at the power supply plus or the power supply minus. Okay, so actually a class D amplifier is a modulated power supply. So you take the power supply to the speaker, either this or the other. You switch by a very high frequency, so the output goes like this. So the output here is very, very, very noisy. Any noise that is on the power supply will end up in the speaker. And the power supplies are normally not very clean. At least in these days when you have a lot of transmitters and wireless and inductive heaters in the kitchen, you have a lot of different things. You have light dimmers, you have, you name it, computers, switching power supplies.
Ja, vaak wordt meegemaakt als je moet installeren bij een klant met een wifi-netwerk wat stoort of magnetrons, liftdeuren die elektronisch op een nek gaan waar die aangestuurd zijn.
But you could filter it or regenerate it.
Sure, you could regenerate it. You could do, but that's quite an expensive solution. Yeah. So for a cost-effective solution, you use the power supply, and you really put the power supply into the speaker. You have some filter here. You have to have, because you would burn the tweeter with this kind of signal. Yeah. So here you have a low-pass filter. And the low-pass filter, of course, has some inductor and some capacitor. A lot of different ways of making this filter, but you must suppress the carrier frequency of the switching amp to get rid of the high frequency. Okay? So then you have some problems. You put something in series between the output and the speaker. So mainly you will lose damping factor. You will lose bass control because there is some resistance in the coils, and you put it between the speaker and the output of the amplifier. So you cannot control the woofers in the same way normally. So there are some, you could do the switching amplifier in many different ways, but there are some basic technology challenges that makes it really difficult to make very good sound quality from a Class D amplifier at an acceptable cost. Of course, if you throw in a lot of clever things, you could make the Class D good. But there are most Class D amplifiers that are good are very costly. Yeah, they are expensive. So. Yeah.
Are there any plans for you if you go big with a lot of power? It's very hard to cool it, get it stable, and you see the most powerful amps are shifting to Class D because of efficiency.
Yeah, but this with efficiency is this is kind of a sure they have a better efficiency, but then again, at what kind of level? At maximum power loss, they have better efficiency, but at a normal level of playing music, there is no such big difference in efficiency, really.
Wow, I didn't know.
There are some differences, but really, you could find the worst power loss for a Class AB is, of course, much worse than Class D. Actually, I forgot to tell about the sound engine technology. Because of the sound engine, we have a power consumption that is about 1/3 the normal Class AB power amps in idle. Yeah, yeah. because we don't need the high bias. I forgot to tell about it. But back to this, you could do this several things to Class D and get better Class D, but we feel that today Class D is not the best solution for cost-effective high-end sound.
But could you apply Sound Engine to Class D?
Actually, the patent of Sound Engine includes Class D. Yeah, it does. So actually, we were looking at it, and actually, what parts of what Devalier is doing is close to what we wrote in our patent many years ago. So it is possible to make combinations of Class D and analog amplifiers that are good, but they are quite complex systems, and it's not possible in this price range to do it. So, but of course, we are following what is possible to do. So, I wouldn't say that forever we will stick with the complete analog amplifiers. Of course, if there are some ways of improving, we will use them, and the patent cover any kind of combination. Yeah, it does.
You said a lot of amps can't handle high res because
Yes.
of the noise floors.
Yeah, and the distortion. Yeah.
And distortion.
Yeah.
Well, Hegel must have a lower noise floor.
Yeah.
Thanks to the sound engine.
Yeah.
And your H360, 160 are all compatible with high res streaming.
Yeah.
Do you think it's beneficial to go high res, or is CD quality enough?
I think it's beneficial, but the main challenge is the master tapes or the source material. Yeah. So if you have good recordings that are taken care of, then of course high-res is nice. Yeah, sure. Yeah. But unfortunately, many record companies, they like to make a new sale with the same old thing and remaster and all this shit. So yeah. But if the source material is good, sure, high-res is very good. Yeah. But still, what I think is, I don't know if Anders played for you on the Mohican. No, I think it will. Yeah. You could play 16-bit with a lot of good sound. Yeah, the sound. So we can still improve the 16-bit. It's quite strange after more than 30, almost 35 years, and we can still improve it. So yeah, it's not about 24 bits everything. So
a lot of hidden gems there.
Yeah, there are. Yeah. Okay.
Yes. Thank you.
Thank you for listening.
Yes.
Thank you.